Let's talk about the the composition of nucleus. And what we understand is that that uh, nucleus has a composition. It's made up of particles, and 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 this thing was as we say it in a general way, that this nucleus was it was discovered by Lord Rutherford, and that's why he's most of times called as the father of nuclear physics. Now, we will not go into the details of the experiment that was conducted by Lord Rutherford, but what he did was that he used the alpha particle scattering experiment. Uh, and this scattering experiment, it suggested that there is existence of some positively charged mass within the region of an atom. If we have an atom, there is a positively charged mass, and this region of charge that was discovered was named as nucleus of the atom. And I think almost all the mass, as on account of those scattering experiments that were conducted, it was observed that almost all the mass of an atom is concentrated within this small volume of atom. And in the beginning, nucleus was it was assumed to contain positively charged particles called protons, and the negatively charged particles called electrons. This was the story of atoms. And however, later on, it was established that electrons they cannot exist inside the nucleus. We have undergone all those most of those experiences where uncertainty principle plays a very key role in demonstrating that electron cannot exist inside the nucleus. So. So electrons did not get their place inside the nucleus, and what is discovered is that they exist outside the nucleus. And then we had the discovery of neutron. We had another particle, neutron. It was discovered, and it was found to have no charge, and this led to the present concept of nucleus, that the composition of nucleus is basically it's composed of protons and neutrons. What we'll come to know later on, we call them as nucleons of the nucleus. Now, if we have, suppose I talk about the atomic number. It is symbolized as Z. This atomic number defines basically the number of protons inside the nucleus. So the number of protons that we have in nucleus, that gives us the measure of this atomic number. So to say, this nucleus has number, what's called as atomic number, and it has mass, and this atomic mass number it is basically this sum of this atomic mass number is given by A, and this atomic mass number is basically the sum of number of protons and sum of number of neutrons. So this Z gives me the atomic number, and this N is a representative of number of neutrons. So if we want to have the number of neutrons inside the nucleus, that's going to be A minus Z. So N is the number, it refers to the number of neutrons here. Now, the atom is basically characterized by the structure of its nucleus here. And, and what we have in nucleus is the number of protons, we have number of neutrons, and then we have the energy content. Then we have the energy content that we are interested in. And and we call these number of protons, number of neutrons, and the energy content that we have in nucleus, we call them as nuclear species, or simply nuclide. So this nuclear species is not generally used. What's used is nuclides internationally. Now these nuclides that we talk about, they are represented by a symbol. So we have a nuclide, and this nuclide has a symbol of X, A, and Z. Now this A refers to the mass number that we talked about, and this Z refers to the atomic number. And there is also a way of writing like this, A and Z. All right. So this X is what it is basically. It is the symbol of the element. So X is the symbol of the element. Now this element can be anything. It can be uranium, it can be hydrogen, and it can be helium. And this Z is, as I said, is the atomic number. That means it's giving us the number of protons. And then we have A, that's the mass number, that gives us the number of protons plus number of neutrons inside the nucleus. So if I take an example of, say, if I write something like this, Na23 and 11, what does it mean is that sodium refers to X is the sodium, and 23 is the number of nucleons. This A is 23, and this is the number of nucleons, and 11 is the atomic number. So atomic number of this nucleus is 11. So this is it. And what we have is we have latest discoveries regarding nucleus. Where we'll not go in details of that, but as a precautionary measure, there are other discoveries that have revealed that these protons that we have, that these protons and neutrons, they are not the building blocks of the nucleus. Rather, this proton and neutron, they themselves are made of some more elementary particles, and these more elementary particles are called as quarks and gluons. Now, quarks are supposed to have frictional electric charge. They have frictional electric charge, and we have 6 quarks, and for them we have up, that is U. Then we have down quark, that is D. Then we have charm quark, that's C. Then we have strange quark, that is S. Then we have top quark, that is T, and bottom quark, and we have bottom quark, and that is and we have bottom quark, that is p. So we have 6 quarks, and uh, and we have the anti-particles of these quarks, whom we call as anti-quarks. So what we have is we have anti-quarks, anti-quarks. Okay, so to say, and we can label these anti-quarks as anti-up, anti-up. So for anti-up, I have U bar, and I have anti-down, anti-down. For that, I have D bar, and I have anti-charm. So C bar. Similarly, we have anti-strange as S bar. We have anti-top as T bar, and we have anti-bottom as B bar. So these are the set of quarks, and these quarks have fractional charges. They have fractional charge. They have charges in terms of fractions, and uh, and if I have to give some examples of if I would like to tabulate it, I would like to have quarks, and I would like to have anti-quarks. So for U we have plus 2 by 3, and for D down quark we have 1 by 3 of E. This is of the fundamental charge the charge of electron or the charge of the proton. So for charm we have 2 by 3 E, and for strange we have minus 1 by 3 E, and for for and we have strange. For strange we have minus 1 by 3. Now for top we have again 2 by 3 E, and for bottom we have minus 1 by 3 E. And similarly, what we have is for anti-quarks, that is anti of the quarks. So for this, what we have is minus 2 by 3 E, and for down I must have plus. It is 1 by 3 E, and for C it is minus 2 by 3, and for anti-strange it is plus 1 by 3 E. For top, anti-top, it is minus 2 by 3, and for anti-bottom we have 1 by 3 E. So this was a preliminary way of giving an idea that we have these protons and neutrons. They are not the fundamental particles of the nucleus. There are particles which are fundamental than that of these protons. These protons themselves are made of the particles, and if I have to take an example of a proton, what is experimentally found is that this proton is made up of two quarks, and which are up, and one down quark that is down. So we have a proton, and this proton is made of quarks, and this proton has 2 up quarks and 1 down quark. So I can think of a proton, and this proton is made of three quarks. So what we have is down, what we have is up, what we have is up. So for this I will have 2 by 3E. For this I will have 2 by 3E, and for down it will be minus 1 by 3E. Okay, so that we have a charge of nucleus equal to plus E. This is the nucleus. And similarly, we have the combination for neutrons in terms of these quarks.